scale setting in QCD. And you often hear, if you hear a LHC talk, they will start out, we don't know how to fix the renormalization scale, so we will guess it. And I'm going to show you that's nonsense. We do know how to set the renormalization scale, and it's extremely important. In this, the way you set it is called BLM, Brodsky, Lepage, McKenzie, but then evolved into what's called the principal maximum conformality, which is an all-orders method for setting renormalization scale. And it makes a huge difference. In the TT bar asymmetry, you see a very large asymmetry in the data, and it agrees with the principal maximum conformality predictions, and it doesn't agree at all with the standard results. So this is work I did with Leonardo D'Aschino, Xingang Wu, Martin Majosa, Shenquang Wang. So the goal in this one lecture now is to show how you can get QCD predictions to maximum precision, and that's really good. Then we maximize sensitivity to any new physics. You obtain high precision determination alpha strong, other parameters. And the point is that we can determine the renormalization scales, and there's often more than one, to arbitrary accuracy without ambiguity. And I'll show you how you do that. But most important, there's no dependence on the choice of the renormalization scheme. You know, the fact that humans on Earth pick MS bar is just a convention. The answer cannot depend on that. But if you guess the scale, it depends greatly on your choice of scheme. So predictions for physical observables cannot depend on a theoretical convention, such as the renormalization scheme, like MS bar, or even the initial scale choice. All those things cannot be true because the physics doesn't care about that. And this principle of maximum conformality, which, and you'll see how conformal invariance comes into this, sets the scales unambiguously at every order. So what I'm talking about these lectures is Poincare invariance. We have causality, gauge invariance, but scheme independence. Physical predictions of renormalizable theories must be independent of the choice of the scheme. And in fact, if you look up the definition of the normalization group, this is one of the key tenets. And however, if you guess the scale, you're violating it. Also, we've been using mass scale invariance, the conformal invariance of the action. That's how, in fact, we learn, in fact, what the right dilaton is and what the right potential is in ADS. So this is an example. I will show you how this works. This is a thrust distribution in E plus E minus annihilation at the Z, and the conventional results never got it right because they just guessed the scale. On the other hand, if you use the PMC, you get the data right on the nose, except right here, which is non-perturbative. In fact, not only that, when you get the scale done correctly, you can take the data from E plus E minus goes to Z, goes to anything, and extract alpha strong of Q squared over a large range of Q squared, exactly what we see from other determinations. So with one measurement at one energy, if you know how to set the scale, you can determine the running coupling over a whole range of scales. And you would never get this right if you just guess. You'd only get 1 point. In fact, there's really, in fact, the scale depends on the thrust, and that means, in fact, you get the behavior of alpha strong. So this is taking data and actually extracting the running coupling a new way. So this goes back to my work in 1982 with Lepage and McKenzie, where we first showed, in fact, that there's really no scale ambiguity in QCD. And then more recently, with Majosa and Wu, we actually developed the principal maximum conformality. There's an earlier paper, too, with Leonardo D'Aschino. And this actually generalizes the BLM method, which was only valid to 2 loops. Now we can do it to all loops, and I'm going to show you how this works. So first I'm going to remind you something elementary. Suppose you do electron-electron scattering in QED. Then you have 2 amplitudes at lowest order, effectively. There's a T-channel contribution, a U-channel contribution. So here I picked all the helices the same. So then what happens is that you put in alpha of T here. Everybody knows this. This sums all vacuum polarization contributions to all orders. It's all, not just this one loop, but every loop. Every loop in the photon propagator is summed into this. It's 1 minus pi of T, where pi is the Serber-Uling vacuum polarization. But this is an all orders result. And then you get another scale, alpha of U, for the U-channel pole. There's not just one scale, there's 2 scales. There's T and U with this order perturbation theory. But this dress photon propagator sums everything. Now, it's conventional to start at alpha of 0, because we know it so well, 1 over 137.03599. However, you can start at any T0. It doesn't matter. This put in the vacuum polarization contribution right here, it's exactly the same answer. So it doesn't matter what T0 is. You always get the same alpha of T. And that means, in fact, the initial guess starting point for the normalization group doesn't matter. However, if you use a different scheme, like MS bar, then you have to actually put in the correct argument of the running coupling. It turns out, when you define MS bar the way Bardeen et al. Do, you have to put e to the minus 5/3 to get the right answer. So this just shows how peculiar MS bar is, that it's off relative to our natural answer by e to the minus 5/3. So these are the graphs for summing alpha of t and alpha of u. There's no scale ambiguity. If you didn't put in this correctly at t and this correctly at u, you'd have to sum an infinite number of diagrams just to recover alpha of t and alpha of u. There's never been ambiguity and so on. It sums all vacuum polarizations, all the non-zero beta terms into the coupling. That's the purpose of the running coupling, is to sum the vacuum polarization, the beta terms. There's two physical scales, t and u. If you choose a different scale choice, you have to sum an infinite number of graphs. However, you will always get the right answer at infinity, but you have to work to infinity. We know the answer in advance. The number of active leptons correctly set. Now, when you put in the leptons here, you have electron, muon, tau, and so on. Well, in fact, you put in the analytic expression for the vacuum polarization, and it goes gradually, and F and L goes from 3 to 4, and so on. Okay. So actually, this procedure of setting the scale correctly sets the number of leptons in the T channel, U channel correctly too. Everything's analytic. It has the right behavior at the lepton thresholds. It's not a discrete jump. It's a continuous analytic jump. But there's never been a scale ambiguity in QED. So here again is summarizing. The answer is two terms, alpha of t and alpha of u. And if you use, in fact, the MS bar scheme, and here's the expression for the relating MS bar to the Serbo-Ewing answer, there's this funny e to the minus 5/3. It's got to do with the way Bardeen et al. Defined the MS bar scheme. By subtracting log of the Euler constant and the gamma function, they forgot to subtract minus 5/3. Then we wouldn't have had this funny thing. But the lesson here is that every scheme choice has a different argument of the running coupling to recover the same answer. The answer cannot depend on your scheme choice. Now, another complication in QED is if you go to two-photon exchange, what happens? There's now two photons. They each share the virtuality of t. So now, in fact, roughly each of these have t over 4. And then there's other graphs. So when each order in perturbation theory, each skeleton graph, if you like, has a different renormalization scale. We've always known this in QED, and we do this. And then the number of leptons that goes in here is less because and so on. Every answer, every scale graph has its correct scale. The normalization scheme dependence, it doesn't matter what scheme you pick, you'll always get the same numerical answer, and it's independent of the initial scale. Now, why is this interesting for QCD? Because actually, if you formally put NC to 0 in QCD formulas, you get QED formulas. That's why it's so important. So there's an analyticity argument that you can go from non-abelian theory to abelian theory by just setting NC to 0. So there's a lessons here. There's never been a scale ambiguity in QED. The Dress photon propagator sums all the beta terms. It's called vacuum polarization in QED. There's a new scale at every order. The effective number of flavors determines. Predictions do not depend on the scheme choice. Once you remember, in fact, to put e to the minus 5/3 in, for example. And we have this NC goes to 0 limit. Now, in fact, actually, Patrick Hunet and I wrote a paper, in fact, explaining this, that when you take the limit of NC goes to 0 at fixed alpha, this is the QED alpha, at CF times alpha strong, it's a 0 over 0 limit. It's very amusing. But in fact, you then recover abelian gauge theory. And you know this, in fact, from the beta function. It starts out 11/3 CA, and as soon as CA is 0, you get the beta function of QED. So in fact, NC equals 0 is the correct answer. But NC can be considered an analytic variable. So whatever you do in QCD better agree with QED in the NC goes to 0 limit. And so I'll do that, of course. But the lesson from QED is all beta terms are summed into the running coupling. So now what you do in this BLM PMC procedure is you identify the beta terms, and then you shift the scale to get rid of them. So first you compute the answer, like right here, any observable in terms of all the different coefficients. There's beta 0, beta 1, beta 2, and so on. And then what you do is, this is the term without any beta terms. This is so-called conformal terms because it's there when beta is equal to 0. Then what you do is you shift the scale to a scale Q1 here, and that actually then absorbs all the beta terms by just this definition. So you just simply match the answer on one side to the other side. It's exactly what you do in QED. You just sum all the vacuum polarizations. Here you're shifting all the vacuum polarization contribution to the argument of the running coupling. And at every order, you get a new scale, and here's the formula. But the question is, how do you identify the beta terms? So here goes way back, and so on. You look at an observable, you have a beta 0 term right here, and then you shift the answer by this coefficient of beta 0, and that shifts you to this Q star. I call it Q1, the previous slide. And then the C1 star is what's left over, which is the contribution without vacuum polarization, is the conformal term. So this is just what we do in QED all the time. But in QCD, you identify the beta terms, you shift the answer, and you put Q star there. And that Q star is the physical virtuality as well when you analyze it. Now the point is, of course, is how do you identify the beta 0? Well, in BLM, we said, look, beta 0 is 11/3 CA minus 2/3 NF. So the NF term is an indicator where the beta 0 is. And in fact, if you just work the first two orders, beta 0, beta 1, that's all you need. So you just simply look at the NF terms and you see all the beta terms, and then you shift and you're done. However, it doesn't work beyond 2 loops, because beyond 2 loops you get all these graphs with 3 gluon coupling with a quark loop and so on. There's 15 different amplitudes, 14 of them are finite in the ultraviolet, so they all have NF dependence. Can't use this method at all. You have to be more clever. You have to be able to figure out where the beta terms are in each and every order. And the theorists who do the calculations, they could do this for you, but after the fact, you say, it's a mess. How do I find the beta terms? Okay. All right, but so here then the trick is you use the NF dependence coefficients to identify the quark loop vacuum polarization. You use this connection, and then you're fine to first 2 loops. And then the coefficient here is the conformal coefficient. So the reason why, again, this is called a conformal invariance is because the right answer has the coefficients, which are the conformal series. Okay, all right. Now, in fact, here, one of the applications I like is that I did with Wang, Kuhn, and Teubner, and that, in fact, shows, that even a simple process like this, E plus E minus goes to quark, anti-quark, and when you work it out, you find actually there's 2 scales. One's of order S and one's of order SV squared, where V is the relative velocity here. So unless you know this, you'll be screwed. But in QED, it's exactly the same answer. There's a soft Coulomb phase type of contribution, and you get both of those in the answer. And that's a very small scale, so even though Q squared is large, you're really sampling the small world. So now, how do we go beyond this simple idea with the beta term just from the NF? Well, this is the trick. Go back to the definition of MS bar. What they did is they said, everywhere you see a 1 over epsilon in dimensional regularization, that's due to 't Hooft, is you subtract, just for fun, log of 4 pi in the Euler constant. That's the convention that people do on Earth. However, we could have subtracted anything. And so we can generalize the MS bar scheme to virtually any dimensional regularization scheme. And you do this with this parameter called delta. So the usual one is delta equals 0. 't Hooft actually likes delta equals log 4 pi in Euler constant, and then you're back to MS itself. However, delta is arbitrary. However, if you do the calculation with the delta, we call it our delta scheme, it identifies the beta terms. So I'll show you how that works. Once you identify the beta terms, then you can actually shift the beta terms into the argument of the running coupling at each order and get you get the right scales, just like in QED, at every order. So then the resulting series matches the beta equals 0 conformal series. The answer at the end is always scheme independent. Once you've got rid of the beta terms, it doesn't matter what scheme you've chosen, you'll get the same physical answer. And also you find in practice that there's really no dependence on the initial scale. So delta here is an arbitrary constant. It's a trick to, in fact, identify the beta terms. And that's what we're going to do. So in fact, here's an example of an observable and so on. You do the calculation with delta in the calculation. You just redo the code, and you get delta here, delta there, delta there, delta there, and so on. And then those deltas identify the beta terms. because that's where they come from. Now, ignoring mass renormalization, which is, you can do it the same way. So what happens then is you automatically then get the beta terms, and you can do this at every order, in fact, and identify the beta terms. Now, in fact, actually, one of the things that before you shift the scales, these series actually diverge by n factorial. That's something that Gardy and other people have emphasized, that the series before you, if you leave the beta terms there, get worse and worse and worse, and you get n factorial growth. So that's another terrible thing if you don't fix the scale properly. Once you fix the scale properly, you get rid of the beta terms. So the idea then is that after you identify these beta terms, so you choose any scheme you want, you choose any initial scale, you use the delta term to identify the beta terms, you shift the scales to eliminate the beta terms, get the conformal series. The answer doesn't depend on the initial scale or the scheme. And the delta scheme then automatically identifies the beta terms. You can teach this to a robot. It will just do it. You don't need to, you can put it in Mathematica, no problem. But then we realized something interesting. We call it special degeneracy. That after you've done this trick with the beta terms, then it turns out that you always find a general pattern of how the beta terms arise as you go from one order to the next order. It turns out it's not as complicated as your first thing. The delta trick exposes this. We didn't know this until we did the delta example. And then we found out, in fact, as you go from one order to the next order, there's only one new term that happens at each order, which involves the beta terms. So as you keep going up in order, you can actually identify all the beta terms one after the other. So I won't go into detail, but it's a neat trick. So you don't actually have to do the delta thing. You don't have to do the computer code again. You can actually just use this pattern. And that's what we do. So then once you've got the beta terms, you then shift the scale to Q1, Q2, and so on with this formula, and you get, in fact, then the PMC scales. So the general result is you have this general result in beta terms, you shift, and you get, in fact, these beautiful formulas to any order. It also puts in the right number of flavors at every order of perturbation theory as well. So every time you put the scale in, just like in that two-loop calculation in electron-electron scattering, those graphs, they have a different number of leptons at every order. This does it automatically. So people really have understood this, that conformal symmetry is really an initial approximation. And then what we do is we then have the non-zero beta terms. But then if you shift the scale, you get rid of it, you get back to conformal symmetry. Also, when you look at evolution equations, like herbal evolution equations, everything is based on conformal theory, where you use the conformal theory as the prototype and then you make modifications on top of it. Also, I'll mention this a little bit down, is you actually get, in conformal theory, you get new relations which you've never believed before could happen. And things like the Kreuler relation. I'll show you how this works. So this allows you, in fact, new ways to relate one observable to another observable without any approximations whatsoever. So you fix the renormalization scale. John Ellis was involved in this. BFKL is all done with BLM, PMC. That's how you identify all the terms that you do with the Pomeron and the BFKL scheme and so on, and so on. And ADS-QCD, of course, is what we've been doing too. So there's no dependence on the initial scale. There's no dependence on delta. Everything, in fact, is actually true. And in fact, this general pattern with delta, I've shown this before, is actually consistent with the idea that observables don't depend on delta. So in the case of RE plus E minus of S, people just guess the scale and they find tremendous dependence on the initial scale choice. You can get any answer you want, basically. However, once you pick the PMC scale, you basically see it's flat. You get the right answer with the experiment, and not only that, you have no dependence on the initial scale as well, just like in QED. So here's actually a list, in fact, of the final scales that appear in the RE plus E minus expression, Q1, Q2, Q3, and so on. When you do the Z goes to hadrons, it's a simple example of the PMC. Right away, you see the right answer here. This is what people guess. They did a good job guessing, but you see actually the right answer is right here, and even at 3 loops and 4 loops, it's indistinguishable. So it's really true that if you work hard enough by guessing the scale, and then you keep doing it over and over and over, maybe you'll get the right answer if you're lucky, but in this case it works. However, it's silly, because if you set the scale correctly right away, you get the black answer, so you're fine. The PMC just does it perfectly. So the features of this procedure, everything is scheme independent at every order. Why is that? Once you pick, for example, in QCD alpha strong at the Z, you're doing it a specific scheme. And then, in fact, once you know that number in that scheme, you put that into the answer, and you forgot, and everything doesn't care about the scheme choice. You match the conformal series. There's no n factorial renorming loss because now the coefficients are the conformal coefficients which don't have betas in them. New scale at every order, NF dependent at every order, multiple scales incorporated. You can just see how that works easily. It's rigorous. It satisfies all renormalization group principles. It gives you a realistic estimate of higher order terms because the higher order terms are not the terms of the beta functions. Those are trivial. They are the new things that happens, like in G minus 2 of the muon, light by light scattering. That's important. That comes into the high order terms. And anyway, it agrees with the NC, goes to the limit of QED. If you do granularification in QED, QCD, and electroweak, you better use the same procedure for setting the renormalization scale for each process. That's the PMC again. So there's no theory error from this. It's unnecessary. Maximal sensitivity to new physics. Then I'll show you commensurate scale relations, which relate one observable to another, which are exciting. And then also this PMC, of course, is the same at the first two loops. All right. So we've done, for example, the Higgs production at the LHC and eliminated the renormalization group equation. You're just doing the usual factorization theorem. The hard scattering amplitude requires a scheme setting. And so what happens when you do it correctly with the PMC is that, in fact, the answer is up here. It's about 20% higher than the conventional guess. Or you just simply say, I guess the scale is the Higgs mass, you know. The right answer is not that. There's a whole series of terms that each have orange scale, and you get this answer up here. And of course, right now the experiment doesn't discriminate. But in fact, here's more examples. People struggling, in fact, with a conventional answer up to next. They never really get up to the correct answer. So in fact, when they finally get very high precision Higgs cross sections, they'll know the difference between this and this. So in fact, there's a dependence on the normalization scale, leading order, next lead order, and next lead order. When you do the PMC, you get flat behavior. Now, here's a nice example. If you do the TT, this is measured at the Tevatron before it closed down. They have a P bar P interactions, and they look at the TT bar, and they look at the backward-forward asymmetry. Because, in fact, the interference of this graph with the one gluon graph gives you a backward-forward asymmetry. It's just like in QED. If you do E plus E minus goes to mu plus U minus, one photon, two photon gives you backward-forward asymmetry. So that's interesting. But you can see right away, in fact, that the scale here, physical scale, the vacuum polarization, everything else that goes in here is different than the scale that appears here, because here the two gluons are sharing the virtuality. They don't have the same renormalization scale. If you guess, what people do, they guess the same scale for every order. Crazy. Doesn't make sense. So the moment you put it in correctly with the renormalization scale, you get the answer which looks just like experiment. If you look this, you're far off. So the conventional behavior is down here for one observable, and this is for the TT bar symmetry, measured for 450 GeV invariant mass, and the measure symmetry is here, and the PMC predictions within 1 sigma. Okay. Now, when you do things like gamma, gamma star to A to C, people always had trouble getting the right answer. However, the moment you pick the PMC scale, you're right on the nose with the experiment. This is typical. We've done maybe 30 applications like this, where every time people thought there was some discrepancy, it's got to do because they guessed the scale incorrectly. And it would have been wrong for QED analogs, everything would be wrong. Now here's oh, please, I didn't hear you. In QED, we always the vacuum pores run cupping. Okay. Well, again, if you think about this delta method, that's the simplest. So you just make sure you identify the beta terms that way. It doesn't matter if you use on-shell, whatever you do. It tells you, in fact, where every beta term is, and the beta terms belong in the argument of the running coupling.
Right.
Yeah.
Who's playing the role of the scale?
Who's playing the role? Yeah. No. Yeah. No. So. Well. Yeah, so the scale, right. So the scale determines, the scale is a physical scale. In QED, it's the actual virtuality of the photon propagator. In the case of MS bar scheme, it's e minus 5/3 times the scale of that. But it's basically the scale that determines the quark loops and so on. But it's not just that, in QCD, it's not just the vacuum polarization, it's the 3-gluon coupling, the 4-gluon coupling, all those quark loops. All those things are determined by the effective renormalization scale, and that's done automatically here. So here's an interesting point, too, is that people have struggled with the thrust distribution. So the thrust distribution in E plus E minus goes to jets. You make this measurement, and people for years have had a very hard time understanding it because they keep guessing the scale is the Z mass. The virtuality of the gluons is not the Z mass. It's much lower. The right answer is going to be here. But the first lesson is that when you use the PMC, you learn, in fact, that the renormalization scale depends on the value of the thrust. It goes from small to up to here values and so on. It's not the same one constant value. It actually depends on the kinematics of the QQ bar glue because the virtuality depends on that. So automatically, the moment you apply the PMC, you don't have to think, it gives you this curve. And now when you put this curve in, you go right through the data. So this is really remarkable, is that, there was never a discrepancy. The discrepancy was because people incorrectly guessed the scale. It's not true. If you put in the right running the scale of running coupling, it varies with thrust, and then you get this answer. Now, to be fair, this group, German, Hoffliger, and Moni, they actually used BLM several years ago, and in 2014, and they were able to explain, in fact, the thrust distribution because they did this right. They didn't. So this is really recovering, in fact, their results. But one thing so after you get this result and it agrees perfectly, now you can say, let's use the experimental data and the renormalization scale correctly set, and then you can compare with the running coupling of QED. So let me go back here. I missed it. Here it is here. So this is alpha strong. This comes right from the thrust dependence because as you vary the thrust, the renormalization scale changes. So when you fit the data, you get alpha strong at all different Q squared. So even though the experiment just measures at one energy at the Z, you actually are sampling the running coupling over a whole range. And miraculously, it looks just like the asymptotic freedom curves we all know. It's perfect. You don't have to, so somebody could have, in the beginning of history of QCD, done this one experiment and said, here's asymptotic freedom. This would have won the Nobel Prize right away for Gross, Wilczek, and Politzer. You do not have to vary the energy of an experiment. You just have to look at the distribution because the distribution depends on the distribution depends on the scale depends, here it is, depends on the thrust, how parallel the quarks and gluons are, what the virtuality is. So I'm just put in these slides because I remind you, in fact, that we were able now with anti-de Sitter space to get the QCD coupling at all scales in the soft region, the Gaussian, and then the 1/log in the hard region, match the two and actually understand, in fact, how you start with the proton or rho mass to get up to the lambda MS bar. So that's pretty neat. But this is exactly the same thing. All right. Yes, please.
Sorry, I have a very naive question.
No, please.
So, when you do renormalization, you introduce, in dim ray, you introduce this mass scale, and like in QED, we would normally set it to mass scale.
Well, QED, we don't really care about the electron mass because you just care about the virtuality of the photon propagator.
Right,
Yeah.
but when you calculate like an observable, the dependence on your mass scale disappears, doesn't it?
Oh, so let's see. Let's say, yeah,
How does this mass scale you choose
yeah.
enter into
No, so if the moment I put the lepton mass in the vacuum polarization, that's a Serber-Euling formula, and that sets the physical effect that changes the photon propagator. That's the famous Serber-Euling vacuum polarization. And that depends on the mass of the electron, the mass of the muon, and the mass of the tau. So that's put in here too, is that you pick the number of flavors by the virtuality of the gluon propagator. And that's done automatically here, because once you fix the renormalization scale by shifting the beta terms into the scale, then in fact that scale actually is the virtuality of that gluon, which allows you to make the quark-anti-quark loop.
When I renormalize, when I subtract off my scheme dependence,
Good.
my
Yeah, so the scheme dependence disappears completely because the answer is the conformal series. There's no reference to the scheme anymore. The beta terms don't have any scheme dependence. So that's beautiful. But then there's the one point, I think, which is what you're asking, is that how do you set alpha strong in the first place? Well, in MS bar, we have this convention that we measure something, the annihilation cross-section, at the Z mass, and then we fit that to give you lambda MS bar to be 0.313 GeV. If you are on another planet and you picked another renormalization scheme, you do the same procedure and you get a different number for the running coupling at the Z. But then if you analyze it, you realize that the one planet and the other planet are all consistent if you make the correct shift between their scheme and the new scheme. Yeah. So it's all consistent.
So then this, but like when you choose this scale, basically, are you improving the convergence? So is this
Yes.
something like,
Oh, for sure.
so is this the point that like, if you were to choose a constant mass scale, your perturbative expansion converges slower.
Yeah, it's worse. It's n factorial growth. If you use the conventional procedure of guessing the scale, you're guaranteed, and Gardy showed this, to have n factorial growth, so it never converges. You get alpha strong to the n, beta 0 to the n, n factorial. The moment you do this procedure, you get rid of the beta terms, there are no n factorial, and you see fantastic convergence. So this is really right. Yeah. Now, the other thing you can do this is relate observable to observable. And you can say, if I measure one observable, I should be able to predict another one. Shouldn't have to go through all this rigmarole. There's no scale ambiguity if you do it correctly. The relation should be transitive. You can go from A to B to C and get the right answer is A to C. Well, these relations are called commensurate scale relations, and I'll show you what I mean. So if you take RE plus E minus, this is known to 5 loops. This annihilation cross-section, but actually, following Grunberg, it's fun to just call this alpha R of Q. This is a new definition of what's called effective charge. It's known to 5 loops in MS bar. So this is actually just a way to parameterize RE plus E minus. When you do the Bjorkane sum rule, the integral of the spin-dependent structure functions, proton minus neutron, you get this answer, but then this is known also to 5 loops. But then you just truncate it. The first term is ms bar over pi. It's known to 5 loops. But just call this alpha G1 of Q. Now, one of the interesting things is these effective charges have the same beta 0 and beta 1. They just differ in higher order. But so far, it's just 2 observables. The question is there a relation between these guys? Okay. So in fact, when you look at it, here's alpha R. I think this is just 3 loops. It's already complicated enough. There's all sorts of terrible numbers in each one. They don't look anything alike. It's really amazing. However, if you actually eliminate ms bar from one to the other, you get incredible simplification. But I'll show you what I really want to do. Here's these 2 observables. I can express one of them, alpha G1, in terms of alpha R at Q star, alpha R of Q star squared with a minus sign, and then plus alpha R Q double cube. You find this immediately. That once you fix the PMC scales, then it turns out there's a geometric series between this guy and the one that appears here and this guy. That's rather amazing. Now, why is this true? It's because actually it was proved by, it was proved by Cruther, who is a graduate student of Gelman, that in fact, if you just multiply out the rate of corrections to E plus E minus and the rate of corrections to the Bjorkane sum rule, you get 1 to all orders of perturbation theory in a conformal theory. This was his proof. This is called the Cruther relation. In conformal theory, there's no corrections to the product. That's really amazing. However, if you now use the PMC BLM scale, then it turns out you recover the conformal series, the 1. However, this scale is 0.52 times Q. So if you make a measurement of RE plus E minus at 0.52 Q, then in fact you get the product is 1. And this is called a generalized Kruger relation because now in commensurate scale relation, because you're relating one observable, Re plus E minus, to the rate of corrections to Bjarke and Summerall at a commensurate scale. There's no rate of corrections, and so on. Now also, because when you set this scale, now actually in real life it's a little bit more complicated. This is just a mean value, because it's really higher order terms are a little different. However, this is basically right, and if you look at experiment, it's right within experimental accuracy. You get this relationship. Also, as you increase the S and you increase the Q squared, you go through new flavors in each virtuality of the gluons. Each loop keeps coming in. However, this compensation puts the flavor changes to be the same. So if you put this root S, put this commensurate scales in at 0.52, they both go through the new flavors, one after the other. So this is exactly right. I mean, this is really so sensible and so straightforward that it's unbelievable that, in fact, humans on Earth have missed this. I mean, any other planet, they've done this already. You know, this is elementary. And it's some striking thing that I've never understood, that some theorist somewhere says, we don't know how to fix the renormalization scale, so we'll guess it. You know, and then everybody adapted that. They didn't think. Say, how can that be? You know, of course you can fix the scale. No problem at all. Actually, I worked with John Ellis and Guidry and Mark Carlin years ago where we discussed the BLM procedure and also introduced the Padé approximate form. Because once you actually see, in fact, that the series converges so rapidly because you have no n factorial anymore, renorm are growth, you see remarkably stable answers, and you can actually use the Padé series to actually, ratios of polynomials to actually extrapolate to infinity. And so you do it here, you get the same answer to very high accuracy. So this is a way to extend the predictions of QCD because you know, in fact, you have a very convergent answer. That was your question before. So that really works. So problems with conventional theory, predictions are scheme dependent. If you just guess the scale, it's terrible. Everything's at every order. You can't repair this at higher orders at all. It's just awful. You don't satisfy the renormalization group principle that nothing can depend on your scheme choice. It's just totally heuristic what people are doing. They guess the scale and then they guess a range for their guess. And very often it's far away from their guess. Doesn't make sense. It gives the wrong predictions for QED. As I emphasized, grand unified theories, you have to use the same scale setting procedure. You can't possibly use something different. The n factorial renormalon growth means there's no convergence of the series. So you can never say, I'm just going to work to infinity and get the right answer, which people often say, I'll guess the scale because it doesn't matter. At infinity, I'll get the right answer. But you can't do it. The series doesn't converge. Okay. Then people are using the same scale at every order. That's obviously wrong. The virtualities change. The guess value of NF isn't right. You have to put that in. And also, I mentioned before, the 3 gluon, it has a quark loop. Well, that has a different flavor dependence. That's all done correctly here. Multiple physical scales have to be incorporated. You get unrealistic estimate of high order terms. Other people say, you know, I present this and so on. People say, well, I like our bad method because we can vary the scale and learn what the higher order terms are. But you only learn about the beta terms. You don't learn about all the other terms in the series. It gives you a completely unrealistic estimate of what the high order terms are. So then you have an unnecessary theory error because we don't have to guess, and you get wrong predictions for many observables, and so it obscures sensitivity to new physics. So it's beyond me. You know, people want to spend billions of dollars and extended time at the LHC. Fix the scale correctly so you improve the sensitivity. Don't put in the wrong answer. You know, it's just amazing. Physical results cannot depend on the scheme. Different PMC scales, no ambiguity. Series identical to conformal series, which converges. The relations between observables are scheme independent and transitive. So we have a whole bunch of examples of one observable to another observable to another observable, which are just primary relations between observables. You don't see initial scale of dependence. And of course, we can identify, first of all, the beta terms using the R delta method, but then after you learn, in fact, that pattern, you don't even need that. Okay, so I think I've said everything here, yeah. So I should mention Kataev, he worked with me and so on, and Lou and Rothman on generalized Kruger relation, and so on. So this is actually then the first lecture. But so where am I in time? So I have a second lecture. I could start now. I don't see. Okay, I'm going to start with my last lecture. Huh? Please go ahead.
So it looks like you somehow fix asymptotic series.
Yeah, you're replacing.
Is there any mathematics behind this? I mean, like,
Well, it's the conformal series doesn't have renormalons. I guess that's mathematics, right? Is that what you're asking? But let's see. But no, I mean, this is the definition of renormalization. You know, when you learn renormalization for QED, you're taught, in fact, that how to put the vacuum polarization into the running coupling. It was the first slide I showed. Alpha of t is 1 over 1 minus pi of t. So it's a series which is actually 1 over 1 minus pi. It's got a Landau pole if you're really worried about large t. You know, so but this is really so the mathematics is simply that formula that you resum all vacuum polarization graphs, proper and improper. That's in QED the one quark loop with a gluon quark photon, every graph, and then they keep repeating proper and improper. Infinite number of graphs are summed into that running coupling. I'm not sure if I'm answering your questions whether that's mathematics or not, but it's a definition of the running coupling that it actually incorporates vacuum polarization to all orders, and you cannot choose any different scale. It's alpha of t. Once you decide to define the running coupling in the Gell-Mann-Low scheme, which is from the Coulomb potential, basically, and alpha of 0 is 1 over 137.03599. There's no other scheme choice. If you pick ms bar, then you have to go back over and actually realize, in fact, that you're off by a factor of e to the minus 5/3 from t, and that's just a simple analysis. Please go ahead. Hi.
I guess, so the other thing that confuses me is that if I'm making a conservative calculation of QED,
Yes.
right?
QED.
Yeah, QED is
Okay.
easier.
Right. And
So if I calculate it through that, okay, no real method. Calculate it one before, right? I have, say like I have the lowest order corrections by photon, you know, the photon value. I don't have to get a prediction which is correct for order alpha squared, I don't have to resum.
but the right answer is that you do resum. Yeah, this is a good point to emphasize this point. Yeah. Right. So let's go back to this. So here, I'm doing exactly what you asked. So here, this propagator sums an infinite number of vacuum polarization graphs. It continues and continues and continues. It's 1 over 1 minus pi. You have to expand this to all orders. All that goes into alpha of t. This is always the way it was. Landau wouldn't have talked about the Landau pole without this formula because, at the lowest order, pi grows like a log, so eventually this hits 1. So, that this is the way you do it. And then, as I said before, at high order, like this graph, you have to put in a different scale.
But don't you have to dress up the say,
Oh yeah. So of course there's vertex renormalization and wave function renormalization, but that's the Ward identity, Z1, Z2. So in fact, the only dependence on the beta dependence comes from the vacuum polarization loop. There is no dependence from the self energy corrections on the lepton line or the vertex lines, because they all in the physical observables you have square root of Z1, Z2 is 1. So that's the Ward identity. So in fact, the only thing you have to think about is actually this. Now there's mass renormalization, and you do exactly the same thing. You can identify the gamma function, which is the analog of the beta function, and sum and then obtain a perturbation theory of the running mass for QED. So, and then you determine it at the right virtuality, P4 vector squared. You want to stop? Yeah. We'll stop for 5 minutes and then I'll continue. Oh, one more thing from Cedric. Okay, this is really, I really want to include this in my lectures. This is such an important topic that's so misunderstood, how to set the scale setting. I grew up in the world of QED where this was absolutely elementary, and I couldn't believe, in fact, that people didn't understand this for QCD. It's really remarkable. Okay, so now let me go back to play here. Okay. All right. So I'm going to continue with a lot of QCD topics now. Again, we're doing fixed light front time, ADS, QCD, and so on. And I'm going to discuss actually some myths, in fact, and that people don't really realize, I think. And that is that, first of all, of course, renormalization scale cannot be fixed. I just spent a whole hour on that. That's really a myth. Of course it could be said. Anti-shadowing is universal. I'll show you what this means. This really has huge impact for nuclear physics. You'll see what I mean. We talked a little bit about initial state and final state interactions, the Sivers effect. People thought for years they must be higher twist, that is, suppressed in the Bjorkian scaly region. There's no extra 1 over q squared. High momentum transfer hadrons arise only from jets. This is another problem. When you do physics, everybody assumes it's a hard scattering formula, quark-gluon scattering. It's not necessarily true. The experiments are more sophisticated than the theorists. Heavy quarks only come from gluon splitting. I'll show you that that's a myth. It's not true. There's other sources of the heavy quarks. QCD condensates are vacuum effects. I'll come back to that. QCD gives 10 to the 42 to the cosmological constant. I'll come back to that. And then QCD confinement in the mass scale from lambda minus bar. This is not really a myth because I showed, in fact, if you start with the hadronic scale, you get lambda minus bar. I don't think you can go backwards. Nobody could ever go backwards. From lambda minus bar, how are you going to do non-perturbative physics that way? You need to know the whole model. So here I could have clicked each of these. Okay. So let me first of all explain to you about nuclear parton distributions, which is probably most of you have not really paid enough attention to this. The data actually shows when you compare one nucleus to another nucleus, the calcium to the deuteron, you find, in fact, that there's a shadowing region. That means, in fact, that you just can't count the number of nucleons in the nucleus. That'd be just this line here. You actually have a depression below 1. And why is that? That's because the virtual photon doesn't get into the interior of the nucleus. And that's called shadowing. One nucleon shadows the other. That's the name of it. But then there's another thing, which is anti-shadowing. Around x.1 to 0.2, there's another miracle, that the cross-section actually per nucleon is above 1. So you get some coherence effect. And it's called anti-shadowing because this goes down, this goes up. And people like Nikolaev and people, they said, well, it must be that the momentum sum rule insists that there's anti-shadowing to compensate for the shadowing here. And that's how they thought about this. So that's been the common wisdom for 50 years, is that anti-shadowing just is there just to compensate to make the momentum sum rule work. But now there's a shock. And these people are heroes, Scheinbein, Capel, Morphin, and Olness and Owens, and they emphasize something fantastic. That is, when you measure deep elastic scattering with neutrinos on a nucleus, that's the charge current reaction, the shadowing is not really different, but the anti-shadowing between 0.1 and 0.2 is missing. The SLAC NMC data that we believe for evermore is above 1, but there's no sign at all for the NUTEB data. And I think other experiments, Minerva has seen this too. So this is really something. Now this should be confirmed and confirmed and confirmed that in fact you don't see the anti-shadowing. The moment you don't see the anti-shadowing, then what happened to this Nikolaev type of argument? That the momentum sum rule has to be maintained. What happened? You know? So anyway, it looks like there's no anti-shadowing in deep elastic neutrino scattering. Is that possible? That in fact the anti-shadowing is different and depends on the probe. That's weird. All right. So another way to say it is anti-shadowing quark specific. That is, does each quark and anti-quark have a different anti-shadowing distribution? And then because the neutrinos see a different combination of quarks and anti-quarks, that's what explains it. It doesn't help the momentum sum rule argument, but it explains why you can get a different answers. So the one question is anti-shadowing non-universal? Is it flavor dependent? And do the nuclear PDFs really obey momentum and sum rules? We've assumed this. I don't know any textbook that even question it. They say, well, of course, the operator product expansion guarantees it. Is that really true? So how does shadowing occur? Leo Sadolsky actually wrote a brilliant paper on this many years ago. And he explained, in fact, where shadowing comes from. And it's interference between what's called a two-step and one-step process. So this sort of illustrates it. I'm thinking of the lab frame where the photon comes in this way, makes a quark-antiquark. Well, that quark-antiquark can just go in and hit nucleon 1 and miss nucleon 2. However, you could see it could also, before it collides with nucleon 1, it could do diffractive scattering. That looks pretty innocent. It looks like just a simple scattering on the... So nucleon 2, let's say, comes first, nucleon 1 is inside. Well, it turns out that this guy has the opposite phase of this guy, and that accounts for the shadowing theory. However, in order for this to work, you have to have deep elastic speed leading twists, no q-squared dependence, and that means, in fact, the nucleon 2 has to be left intact. And that's called leading twist diffractive deep elastic scattering. And so I'll show you how this works. But now I'm going to show you, in fact, that when you include not just the two gluon exchange, but include quark exchange, which is the regyon exchange, you get, in fact, non-universal anti-shadowing. So first of all, let me tell you about something that you don't maybe know, which is called diffractive deep elastic scattering. The electron, for example, can keep the proton intact while, in fact, creating a whole bunch of stuff here. So this is arbitrary q-squared, but the proton is left intact. It can even happen on a nucleus coherently, but this is the main idea. In fact, there's data. This has been measured, in fact, carefully, in fact, H1 particularly. And so what you see, in fact, is actually you measure the structure function where there's a large rapidity gap and the protons remains intact. And there's no q-squared dependence at all that would tell this higher twist. You can see it's there forever. So how does it happen? Well, the way it happens is a lot like the Sivers effect. The protons, one of the quarks can emit a gluon, can make a quark-antiquark pair. The photon hits that. That's just a C-quark contribution from deglap evolution, say. However, in the final state, the quark here, the struck quark, can interact with the spectators. Now, why is that interesting? It's because it neutralizes the color, right? And the point is that this final state interaction is leading twist. It doesn't go away. You know, when you're taught the Parto model, you say there's no final state interactions. If there is any, they're power law suppressed in q-squared. Not true. So here's a little bit more of the analysis. You have the gluon that splits into quark-antiquark, beta 1 minus beta for the light front fractions, and then you exchange this gluon. Now, normally it'd have, in fact, a mess here because it's two gluon exchange. But because it's two gluon exchange, the two gluons can leave the proton intact. Some momentum transfer, but it's there. And these two gluons leave a rapidity gap. In fact, this simple analysis explains, in fact, all the data, explains all the curves and so on. So that's what we're really seeing, in fact, is this thing. And roughly 10% of the data that's measured at high energies is diffractive deep elastic scattering. This is a very important channel, which leaves the proton intact with a rapidity gap. So here again is the theory. Here I've missed N1 and go into N2. Here I do diffractive on N1 and then break up N2. So there's interference of two-step and one-step process. But the interesting thing is that when you do the phase, they're opposite in phase. The reason why they're opposite in phase is because one of them is a Pomeron exchange that gives you an I. There's another I from the cut, and you get I squared, which is -1. So in fact, the data that shows this shadowing, in fact, is understood, in fact, from the interference of the two-step and one-step process. And then what happens, though, is that when you put the regyon contribution to this diffractive contribution on N1, which is quark exchange, regions in the T channel, then you get a different phase. And then that phase turns out to be constructive in interference, and that's how you get, in fact, anti-shadowing. So this is pretty ugly. The interior nucleons now are anti-shadowed. The Reggie exchange produces a coherent constructive interference, and you get anti-shadowing. So a little bit more on this is that there's a famous relation called the Kuti-Weisskopf relation, which tells you, in fact, if you measure the structure function on a proton minus a neutron, then it goes like the square root of x. That square root of x just comes from the regyon exchange in this graph. You put in a regyon in the T channel, and you get the square root of x. This goes way back from 40 years ago when people understood this. And here's the data. You actually see the square root of x behavior beautifully when you take measurements and so on. This is just what you expect from Reggie behavior. And it's called the Kuti-Weisskopf effect. So now, when you do these interference graphs, you have not only gluon exchange, but quark exchange. That's the thing that gives you the region. And that, the interference between the two-step and the one-step, this is a two-step process, diffractive on one guy, non-diffractive the other one, you get a coherent effect. And here's where the signs go. The phase of the two-step amplitude, first of all, involves the region contribution. There's a thing called the signature factor. So if you're at alpha of a half, maybe Adam will explain this, you get, in fact, this phase 1 minus I. And then when you multiply this by I, which comes from the cut, it turns out you get constructive interference. So this is, in fact, how you, in fact, get to have this effect. But let me just say one more thing before showing this, is it depends on the quark flavor, because the regions exchange isospin. So, in fact, they get a different answer for each quark. So now we see, in fact, why the neutrino experiments could be right. The photon Z0W, each of them have different combinations of quarks, and so you get different answers. So with Liu and Schmidt and Yang, we did a lot of exercises of this. We can see, in fact, how the sine squared theta determination can be wrong by Nutev because they didn't allow for this. All sorts of interesting things. And you actually see different anti-shadowing curves depending on which quark or anti-quark you hit. It's fascinating. There's, it's a whole world of physics in the PDFs that we don't appreciate. And if you use the photon currents, you get one thing. You use a Z current, you get another. Everything is different. So again, what we're doing then is you're looking at this two-step process where it's diffractive through two gluon exchange or quark exchange. If it's two gluon exchange, it's shadowing. If it's quark exchange, it's anti-shadowing. And it's this two-step process, diffractive on the front phase nucleon, and then non-diffractive in the second one. And so what's happening is actually the front guy, this guy here, is actually creating another flux which hits the interior. They're out of phase, and that's called shadowing, because the interior ones don't see the original beam. Now comes the most amazing fact. Suppose you consider that deep elastic Compton scattering, forward virtual Compton scattering with two virtual space-like photons, just a theoretical idea. Then, in fact, this graph, if you take its cut, is, in fact, the usual argument for how you do the parton model. You do, in fact, you take the handbag diagram and you cut it, you put the operator product expansion for these two photons, and you derive, in fact, all the relations of the parton model from the operator product expansion. But now you have a problem. Because in this graph, which is the interference of the two-step and one-step process, the cut of this is what you measure, then you see, in fact, that this photon can't get close to this photon because it's actually trapped between N1 and N2. The analysis is not the handbag diagram anymore. Even though it's leading twist, the handbag diagram is wrong. It's not that the two photons land on the same quark and then use the operator product expansion. That's too simple. The photon here is always, never gets close to this one. So no matter how high Q squared is, these guys do not contract to a point, and you can't use the operator product expansion, and there goes the sum rolls. So as far as I can tell, it's a total myth that nuclear PDFs obey sum rolls because of this process. The shadowing and anti-shadowing is totally a new phenomena, and it doesn't really work. So there's crucial experiments that people should be doing. They should be measuring, even at JLab, at 12 GeV, they can be measuring diffractive deep inelastic scattering. Can you explain with that diffractive, do you get the right number for the observed shadowing? It does work at higher energies. I've checked that myself. Isospin dependence of diffractive deep inelastic. They can actually see processes which are diffractive, however, the proton changes to a neutron. They can look at that. That's right here. You can also see then the flavor dependence of anti-shadowing. You can tag each quark in deep elastic scattering and then measure whether anti-shadowing is there. And then there's another thing, which is Autoron exchange, which is another thing. Besides two gluon exchange, there's three gluon exchange. And that produces interesting physics, and I'll show something. So now, going back to a previous slide, we talked about how most everything is controlled by the wave function, the light front wave function of the proton, or the nucleus, or whatever. And you get all these right results. However, the moment you put in final state interactions, you've lost all the direct connections. You have to modify your answer. You have to put the Sivers effect in. You have to, shadowing and anti-shadowing are involved diffractive processes, which are like this. So here's the problem, that the observables do not really match the square of the light front wave functions until you put together these rescattering lensing corrections. And then, as I emphasized, some rules are never been proven. And this is, of course, what's measured. So this is controversial, what I'm saying. I don't think anybody on Earth besides me is yelling about this, you know? I'm saying over and over again, watch out for the nuclear PDFs. They really are a hint that things are much more complicated than you thought. And this data, this NUTEB data, that doesn't show anti-shadowing, that should shock everybody, that nobody ever anticipated that, you know. So again, what is the physics here? The Sivers effect, we look for this T-odd, pseudo-T-odd effect. You see it in the data. It exactly comes from this diagram. Again, rescattering. The same diagram that produces the Sivers effect produces diffractive deep inelastic scattering. And then, very briefly, there's a double Bohr-Moldes effect. When you do Drell-Yan processes and you put in QQ bar goes to mu plus mu minus, but then you allow for gluons to interact with the spectators, that's the analog of the Sivers effect. Then if you do twice, two of them, you get what's called the double Bohr-Moldes effect, and it creates havoc. It changes the angular distribution. You know, Drell and Yan predicted 1 plus cosine squared theta. In fact, the data has a huge sine squared theta cosine 2 phi term, and part of it can be understood from hard gluon radiation, but part of it from the double Bohr-Moldes effect. It totally complicates your analysis of things like the angular distribution of the Drell-Yan process. That's interesting. And then Collins and Shu wrote a brilliant paper where they point out, suppose you're doing charm production through say, valence quark annihilation and PP bar, and you go to CC bar. Now you have initial state interactions that creates a Sivers effect in the initial state, creates double Bohr-Molders if you put 2 there, and now you have, in the final state, you have CC bar interacting with the spectators. This totally destroys any possibility of factorizing some observable. And to go from one process to another process, that's their paper. The paper is entitled Breakdown of Factorization Theorems, and they illustrate it with this. You know, when you have the combination of both the initial state and the final state, you're dead. Okay. Any questions? Anybody want to say something? No. Okay. So I will just refer, though, I wanted to change subject quickly. Al Mueller and I developed a theory of color transparency. What is that? Well, it says, in fact, that a proton, if it's shot out of a nucleus, it can interact weakly. And the reason why it can interact weakly is because it's at high Q squared, it's born with all the quarks close together. They have a small colored dipole moment, and they go right through the nucleus. So this is called color transparency. Anytime you have a process, a hard process, where you're sampling the wave function, where the quarks are close together, they can go right through a nucleus with hardly interaction. And that's called color transparency. So you just get Z times this. And this has actually been confirmed. So there's all sorts of processes like this. It's really a fundamental test of gauge theory, because the reason why the color dipole moment is so small is because you're interfering diagrams where the gluons hit different quarks and they interfere destructively to give you a small answer. And the small color dipole moment interacts weakly. So you get coherence effects you didn't expect. There's many tests and so on. Then there's another experiment here. This was done by Daniel Ashray at E791. He led this group. You have a 500 GeV pion that comes in and makes quark jets on a nucleus. And the diagram you imagine is 2 gluon exchange, which materializes the quark and anti-quark. This is worked out by Frankfurt, Miller, and Strickman. And now the idea is, in fact, that if you look at the jets, which have high K perp, it means it came from the hadron, where the quarks happen to be at small b perp. And so then you can pick out those guys, and then you should see an amplitude that goes like A or A squared when you do the answer. And so this was looked at by Ashray and so on. They didn't go out very far in K perp, but already you could see the sign that you're nowhere near the Glauber answer. You actually get, which is 0.7, you get numbers which are much higher. So eventually it's going to reach the power 2, which is the ultimate. Also, what's interesting about this is that you can point out by Frankfurt and Miller and Strickman is that you can actually measure the wave function of the pion, because the quark and anti-quark, if you trust your localization of the quark axes, it tells you, in fact, the K perp dependence, and then you have the x and 1 minus x of the quarks. They center around x equals a half, And then you see, in fact, that as K-perp rises from this region to this region, it becomes a little bit narrower. It's just what you expect from the faster fall-off of the perturbative answer versus the Gaussian fall-off out here. So there's a possibility, I really wish they do more experiments. They could actually see the Gaussian behavior, which comes from light front holography, and change into the perturbative answer at high K-perp. Now, actually, one of the things I've been thinking about recently, which is really fun, is that in principle at JLab, they can make positronium beams. They can make relativistic positronium beams, say 10 GeV, and they can scatter in a thin target and then materialize the positronium into electron-positron. And then you can identify X and K-perp and 1 minus X and minus K-perp straightforwardly. You know, these are the frame-independent variables which actually measure the wave function, X and K-perp. Again, X is what we all know now, the light front fractions. But would you actually, because it's one photon exchange, you get the first derivative of the light front wave function. In the case of the QCD, it's two gluon exchange, so you get the second derivative. So actually, you can measure the wave function in atomic physics by this experiment. But it's more than that, because you can actually produce extra Fock states. The entire, positronium is much more complicated than E plus E minus. It's got higher Fock states. E plus E minus photon, E plus E minus 2 photons, E plus E minus, and so on. And all those are measurable. So I think that's pretty interesting. So you can measure the light front wave functions of atoms this way. I never heard of anybody even proposing that you can measure wave functions in even atomic physics. They always think of it as a mathematical object. It's actually, you can measure it. And then you see the transitions between the 1 over K-perp to the K to the fourth, which is the Bohr wave function, to the 1 over K-perp squared, which is the perturbative answer. That would be fun to see that. If you go to the non-relativistic limit, it's the Bohr atom. The wave function is, K squared plus P perp plus alpha M quantity squared, whereas in the perturbative region, because of hard photon exchange, you get 1 over K-perp squared. So you can actually see the transition from non-perturbative to perturbative, if you like. Higher Fock states, I already mentioned that. In the case of the deuteron, I've talked about this before a little bit, that the deuteron actually is much more complicated than a proton and neutron. So if you dissociate it, just like the Ashray experiment, at high energies, you'll see all sorts of new phenomena. 6 quark jets, 3 diquarks, all sorts of possibilities. So it's a whole new way to actually look at physics. Going back to QED, for example, though, suppose we had this wonderful beam of 10 GeV positronium, and we collided on a proton target. This is my favorite experiment now. Hopefully they'll do this in the next couple of years. This is just so amazing. What you can do is the positron can scatter one way, the electron can scatter the other way, leaving the proton basically forward with a very small momentum transfer. This is deeply virtual Compton scattering. It's the matrix element of 2 currents, but for 2 space-like photons. This has never been done before. We've never even thought that you could measure Compton scattering with 2 space-like photons, and they're basically equal. So this is actually a wonderful thing, because why? Because you want to know this for example, the muonic hydrogen Lamb shift, which depends intimately on this graph, the 2-photon exchange graph between the muon and the proton. So people think it's the radius problem of the proton is the problem, but it's also how you calculate the 2-photon exchange with the proton. And this involves the D term and all the J equals 0 fixed pole, all this interesting stuff. So actually, you're measuring this thing. I made a joke here. It's like making a movie because it's on the light front. As each of these guys collide, you're not measuring at one time. You're measuring along the front of the light wave at 2 different light front times. It's just brilliant, I think. They could do this. Now I'm changing the subject. So Ann Stickles is actually a hero of this thing. She noticed, in fact, in the Phoenix collaboration, something is startling. That if you measure the ratio of proton to pions in PP collisions, for example, here it is right here, then what happens, see stars, is that there's, of course, more pions than protons, as you might expect. At high PT, here PT of 4 is high PT. And then she looked at peripheral nucleus-nucleus collisions. And again, it's the same answer. That's the red dots. However, when you look at central collisions, where you get this huge multiplicity, there's more protons than pions at high PT. Totally backwards. I think, people just fell off their socks to imagine how this could be. That in fact, you're way out here, you get more more protons than pions. How can that be? Well, the reason why is because protons, if you look at their power law behavior at fixed xt and theta center mass, it doesn't scale as 1 over pt to the fourth, it scales as a much higher power. And the reason is because it comes from a higher twist process, and that higher twist process produces the proton isolated with high PT with a small color dipole. And so the proton doesn't get absorbed. So this could be color transparency. It's really a fascinating topic and so on. Deserves much more study. And I think is a central thing at RIC. So, this is very interesting. Again, peripheral collisions look just normal. Central collisions, which are high multiplicity, where you hit head-on, have this unusual effect. So protons are somehow less absorbed in nuclear collisions than pions, because apparently they're color transparent higher twist processes. And one of the things that confirms this is that Sickles looked at the proton, and it doesn't come from a jet. If it was a jet, you'd see a lot of particles along the same wave. Like if it's a gluon jet, it makes all sorts of quarks and gluons along the way. There's none. The proton's made isolated, and that's another thing which is interesting. Michael Tannenbaum called this the baryon anomaly because it's so strange. Needs to be explained. Okay. So summarizing, what it is that we already know, in fact, from data that there's anomalous dependence at fixed xt, that you get higher powers than just the simple scale invariant powers. The protons come from these direct subprocesses. Pions come from fragmentation. Protons do not come from jets because you don't see the same side hadrons. They're less absorbed because of color transparency. And then you get, in fact, this observation. So I'm not saying we got the right answer, but this is a logical explanation, in fact, of what's going on. But anyway, it's much more. Okay, I talked before about the deuteron as a 6-quark wave function. It's actually much more complicated than proton-neutron because there's 5 different color singlets, which are you take 6 color triplets, you make a color singlet. And only one of the states is the NP. So the deuteron is built of much more complicated states than just the proton-neutron. So in fact, you can actually see the effects, first of all, in counting rules. So this is now deuteron photodisintegration. This is gamma D to NP. And the prediction is it should fall off like S to the 11th if it comes from perturbative QCD. All the diagrams do this, right? And you get, in fact, exactly the data. It's pretty amazing. If you like, this power law behavior is the underlying conformal invariance of the theory. Predicts this 1 over S to the 11th. Every process, you just count the number of quarks, and you get the right answer. So the deuteron comes in. Normally think of it as 2 clusters, 2 color singlet clusters. Each of these is a 3, of course, make a color singlet. And then you think about it as that there's a wave function for the proton, wave function for the neutron, so neutron, proton, and then there's a so-called body wave function, which actually connects the 2 clusters back in. In fact, one of the nice things about the front form is this cluster decomposition really works. You can actually define this without any trouble, how you, in fact, sum all the diagrams here, here, and here, and so on. These factorize out properly. It's all because the complication of numerators is gone. The only thing that changes is the denominators, which is m squared, the change of m squared, and that's why it's so simple. So you actually, again, look at fixed light front time. But as I said, this is not the end of the world because you can exchange a hard gluon between any of the 6 quarks. The moment you do this, you get a new evolution equation for the 6 quarks. And this is then called the perturbative QCD evolution of the deuteron distribution amplitude, and you can work it out. You can work out the asymptotic form where they all become equal. You can just follow it along with perturbation theory and see, in fact, how the gluons take you from one of the states to the other states. In each case, all the states satisfy the sum of k perp is 0, sum of x's is 1, and so on. And then you get this masterful 6-quark wave function, which has got all the 5 different color singlets in it. So the deuteron is an interesting QCD object. It's got a 6-quark wave function. The components evolve towards equality at short distances. The hidden color states, though, really come in to every time you do a high momentum transfer. So I'll show you that. And, I forgot what this is. I have to fix that. Okay. And then you also get this phenomenon. You can also work out it asymptotically. The deuteron becomes a very small component of NN, partly delta delta, and partly hidden color, mostly hidden color. Now, when you do the electron scattering on the deuteron, the form factor, then it's very interesting because the deuteron is now forced to change from P to P plus Q. So in general, it's the Drell-Yan-West form, it's just the overlap of light front wave functions. Now, if you assume the clustering decomposition, then you get this formula. You get the formula for the proton form factor. You get the amplitude goes like the proton form factor at T over 4, the neutron form factor at T over 4, because it has to change from P over 2 to P plus Q over 2. So what's nice to do is you take the observed deuteron form factor and divide by these two guys, which takes out the compositeness of the proton and neutron. So now after you remove this, you expect FD looks just like a pion form factor, just a quark anti-quark. And it should fall just like 1 over Q squared. That's the prediction. So you define the reduced form factor by doing this trick. Well, in fact, actually, this experiment was done. It's really Ben Chertock's group, American University. They did this at SLAC years ago. And Lepage and G and I gave detailed formulas, but we predict, in fact, 1 over Q squared for the reduced form factor with a logarithm modification, and that's just what you see. If you multiply out the monopole, which is 1 over Q squared, then you get a constant behavior. So you really see, in fact, the FD having the right behavior. But if you work out the normalization, assuming a 2.2 MeV bound state, you're nowhere close. It's much too small. This is a much bigger effect, in fact, than that. And the reason is because once you get into the high Q region, you're looking at the higher Fock states, which is the hidden color Fock states. So here's a picture of it again. You pull out the monopole, which gives the right behavior, and then you get this constant behavior. I think this is very exciting. You know, this is really a beautiful thing that shows, in fact, that you can really see, in fact, in something as complicated as the deuteron, the scaling law is a conformal theory. But then the magnitude of this thing is much bigger than you ever would expect from the cluster physics. And also you can predict the ratio of delta plus, delta minus, and so on. All right. So going back to the proton, it's got when you decompose it on its valence Fock, the wave function on its Fock states, you get the valence 3 quarks in a gluon, 3 quarks, quark, anti-quark, and so on. And then the issue is, what is the structure of these higher Fock states? They have strange quarks, they have U bar, D bar, they have strangeness, charm, bottom, all in these wave functions. It's pretty interesting. So they're not just trivial valence wave function physics, and it's not true that they only communicate with the other quarks by gluon splitting. So you'll see this in a moment. Also, if you look at the data, S bar is not S, and U bar is not D bar. And of course, the deuteron I already told you about. Well, here's a beautiful curve of D bar over U bar. If you thought that the C quarks come from gluon splitting, you get 1. Nothing like that. You know, the D bar over U bar is totally different than what you'd guess. And the reason why is because the quarks in these Fock states are continually interacting with each other. They're all being confined in the 5 quark wave function. They're interacting. They know they're in a proton, not an antiproton. They know, in fact, what the valence quarks processes are, so you can understand that. But then the question is, what about the heavy quarks, like charm and bottom? Surely they only come from gluon splitting. That's the usual dogma. But that's not even right. Even in QED, you don't get that right. So let me explain. So let me go back. So the gluon, normally what you have in your mind is that everything comes from gluon splitting. That's your intuition. Yes, hi.
Can you comment on the slide before? The one with, yes. So the two curves, the purple and blue, are like the standard PDF parameterization.
Yes.
They are completely out.
But this is from these different experiments. I'm not sure if I understand your question. Okay. Yeah. So I'm just reporting the experimental results. No, the band is from an experiment that gave a band. Yeah, yeah, yeah. Okay. So now, is it true, in fact, that everything comes from gluon splitting? Strange quarks and so on. But people forget this graph. Suppose you think about the proton for a moment. It has this graph with a quark anti-quark, and If you cut it, you get the 5-quark Fock state, in addition to the gluon splitting. It's another contribution. It's, in QED, it's called light-by-light scattering. In QCD, it's actually, you get a G, it comes right from the G cubed term as well. So when you count when you figure out how it depends on the quark mass, it's not logarithmic, that's deglap. It goes like 1 over mq squared in QCD. In QED, it's 1 over m to the 4th. If you go from this light-by-light scattering graph and you put in electrons, muons, and tau, it goes like 1 over m to the 4th, because that's just the insertion of the usual light-by-light scattering graph. So what are we doing? We're just cutting the graph. The square is that self-energy diagram. And so the moment you put in the 2 gluon interactions, it's totally different than 1 gluon, because now the wave function likes to put all the particles at the same rapidity, and that means that the the heavy quarks have most of the x. It goes like what's called the perpendicular mass, mq squared plus k perp squared. So the moment you put in these diagrams, they have a completely different nature. Instead of x being very small, like you get for deglap, these are very large x. So there's 2 components. QCD predicts what's called intrinsic heavy quarks at high x. And that's because they like to be at the same rapidity, which is exactly the same as minimally off-shellness. The 5-quark Fock state is off-shell, but it falls off quickly with off-shellness. The minimum off-shellness is exactly when they have this behavior. All right. So you have then the diagrams like this. You get a large X effect and so on. And now you get new things like Higgs production at high XF. So I wanted to show you this because it's so interesting. So the first thing is, it's really astonishing that in 1983, people measured the charm structure function. This is the EMC, European Muon Collaboration experiment. And they found this remarkable result that at x of 0.42, q squared is 75 Jeb squared, the data is far away from what you get from gluon splitting, deglap. It's much bigger. It's a factor of 30 times bigger. And as far as I know, nobody's ever measured the charm structure function ever again since 1983. People can correct me, but this is not such a hard experiment, guys. Why don't the EIC, right? This is fantastic. You see charm and bottom at high x. This is exactly what you predict from those light-by-light scattering graphs. And somehow, the community is so sure it can't happen, they don't even bother to check this. It's built into all the textbooks and so on. The only way to make the charm quarks is gluon splitting. That produces the charm quarks at low x. However, the moment you put the intrinsic charm contribution in, it's at high x. So there's 2 contributions. They each evolve separately. One's the extrinsic, which is just the simple glue splitting, and the other is the intrinsic. So here's something, though, that actually people measured, in fact, at pp bar at the Tevatron. They measured, in fact, photon one way and charm the other way. And they found, in fact, that the charm cross-section is much bigger. Photon on one side, charm on the other. Much bigger than they ever expected. That's because they forgot the intrinsic charm contribution. However, the bottom contribution looks normal. And the reason why it's normal is because there's a 1 over m squared. It's 1 over mb squared. It's 10 times smaller. If they look carefully, they'll eventually see, in fact, the bottoms start to go up too. Now, there's other ways to see intrinsic charm. This goes way back to Barger, Halsen, and Kuhn. They looked at all the data in the world for D production, lambda C production. It goes all the way out to high XF. Lambda C's, if you believe the intuition, they could only be produced at low X because the charm quarks carry such a small fraction of the proton's momentum. Not true. The intrinsic charm puts it way out here. And there's many experiments like this. People have measured J psi at high XF, double J psi at high XF, lambda C's at high XF. Lambda B was discovered at high XF at the ISR. The Sellex experiments, which discovered the double charm variant, is high XF. That's the natural domain for the heavy quarks making hadrons. So what's happening? The pion comes in, for example. It goes into its Fock state. It has intrinsic charm. It makes a J psi at high XF. The lambda C, you look at the intrinsic charm Fock state. The C, U, and D coalesce. They're at the same rapidity. They make the lambda C. And there's a whole bunch of measurements by Sellex where they measured for different beams, And they got exactly the right power law behavior at high XF and so on that you expect. The power law is controlled by the spectators you left behind. You can't go to x equals 1 because the other quarks are there. You put that in. So anyway, if you do deep elastic electron scattering, this could be for the EIC, for example. You collide the electron with the proton. You can see downstream both the lambda C and the D meson. So that's interesting. And so on. And the lambda B and the B, in fact. You can see both, in fact. Okay. In fact, actually, this is sort of amazing in history of science, is that the lambda B was discovered by this group who's led by Ciaffarelli. Here she is. And this group, in fact, discovered the lambda B. They discovered it's the BUD state. And she discovered it with 2 different decay channels, high XF, and the particle data book refused to put her entry into the particle data book because they didn't believe it's possible that a bottom quark could be at high XF. Come on, guys, it's the way it's naturally made. You know, and then what happened? UA1 discovered the lambda B at the same mass that Ciaffarelli found in this experiment, exactly the same number, and then they finally put her discovery in later on. You know, but they had such a prejudice in their mind. It's interesting for all you guys, you young theorists, right? Experimentalists. Don't be fooled by common wisdom. You know, that's the trouble. Common wisdom is often wrong. B quarks are not just made at low X, they're made at high X. Okay. Now here's another thing which is interesting too. People measure proton nucleus goes to J psi plus anything, and they did it on different nuclei. And then they found this amazing result that actually as a function of X Feynman, as you keep going, the J psi takes more and more momentum of the proton, you get this unusual behavior like this with a power law like 8⁵ out here. So how do you get this strong nuclear dependence for fast charmonium? And I'll show you, there's only one real explanation of this. It violates perturbative QCD factorization, because if you just try to put in ordinary subprocesses, you'll never get this effect. But what's really happening? Well, if you have the intrinsic charm Fock state connected by 2 gluons, then in fact, this state has got lots of color. It's a very colored state. However, the moment it interacts by gluon exchange with the first nucleon, it changes this color to a color singlet, and now the color singlet can go right through the rest of the nucleus without interacting. So the cross-section goes like the number of nucleons on the front surface, which is 8⁵. And that's how you can understand, in fact, why you get this strange behavior, why you see only the front nucleons actually produce the J psi, because of now color opaqueness, not color things. So you do see this 8⁵. Okay, then intrinsic charm produces the Higgs. So this is so straightforward. The proton we already know has CC bar. You see it in J psi production, lambda C production. You see lambda B production, that's BB bar. And the Higgs loves the heavy quarks through the Chikawa coupling. So it actually takes the C and C bar momentum fractions, x1 and x2, and adds them together and gives you xf, and produces the Higgs way out at high xf. So this is a completely different way to produce the Higgs. It's downstream. The Higgs have most of the momentum of the protons at the LHC. That's interesting. Okay. So actually we computed the cross-section zone. It goes up to 50 femtobarns. And you can see, in fact, that it loves to be XF about beyond 0.8. It's huge. And we included actually both the charm contribution and the bottom contribution, because the bottom is down by 1/m², but the Higgs coupling is up by m². So they're basically equal. And we even try to estimate the top quark, intrinsic top quark, which is sort of funny. All right. So intrinsic heavy quarks, things that for the EIC and also JLab can do a lot of this, is you could make sure you understand S naught, S bar, all the intrinsic heavy quarks, guys, the role of color confinement in deep elastic scattering. Well, I'm sort of give you examples of this. Hadronization at the amplitude level. What does that mean? Well, what it means is, in fact, that using the light front wave functions, you can actually start with a quark gluon intermediate states that are off shell, and then sandwich them onto the light front wave functions to get the hadrons. Nobody's done this yet. It's got to be done. Okay. Then, in fact, there's all these effects of leading to us lensings, like the Sivers effect. There's diffractive deep inelastic scattering. I've referred to static, which is just the square of the light front wave functions, versus dynamics, which includes the lensing effect. Now we have this whole new world of shadowing and anti-shadowing, which is much more sophisticated than we ever thought. Apparently, anti-shadowing is non-universal. That means it's flavor specific, and so on. Also, even at 12 GeV, JLab can produce charm states. Like, here's a simple example. If the photon produces CC bar, makes a D lambda C. I don't know why they're not looking for charm states. I haven't heard of any experiments yet, and so on, but this is well within the kinematics of the 12 GeV program. And there's already hints from Cornell experiments and so on that there's much more at threshold charm than people believed. So that goes on and on. So anyway, there's also interesting things you can do. You can produce a J psi and a proton in the final state, and then you can wonder whether the J psi binds to the proton. Is it possible, in fact, that you get a J psi proton state? This is really a pentaquark with CC bar and UUD. In fact, there's no reason why, in fact, JLab can't start looking for this type of thing. It's within their kinematics. And it's the van der Waals attractive potential that does this, and so on. And so then you can form these beautiful bound states. So you can even do it with nuclei. So this is another thing, is that you can actually take a nucleus and leave a proton behind. You can actually take one of the nucleons out, and you can produce a J psi with a nucleus and see whether it binds. Well, that's interesting too. The A to C could bind with a nucleus to the van der Waals potential. And as far as I know, and this is something that Manahar looked at too, those states should be there. There's no reason why the attractive potential between the J psi and the nucleus doesn't work. So J psi physics and threshold physics is really interesting, and you produce even tetraquarks, J psi bound states, pentaquarks, all sorts of things. And even my favorite idea, the octaquark, as I told you about last time, that there's even in states, in fact, which it's got 3 up quarks, 3 down quarks, and a CC bar. So then you get tetraquarks at threshold. You can do this. You can produce the 4-quark state. So that's all there, and so on. And here's another thing, too. Along the proton direction, you can make another type of tetraquark, which is CC bar, UD bar. I will skip this, I think. All right. So there's a lot of things that can be done before we look for the electron-ion collider. Lots of interesting physics. Nuclear bound quarkonium, charm at threshold, dramatic spin correlations, in fact, and so on. Now the Autoron, I'll mention that. I have a couple minutes, I hope. I don't know, where's Elena gone? Am I talking too long? You have to stop me. What happens at the Autoron is never been observed. However, what people could do is look for a photon produce a pi zero through 3-gluon exchange. And this actually is possible, and you might get these interesting contributions. Isospin 1 goes isospin 1. And then because of the charge conjugation is different, you need the 3 gluons. But also what's also interesting is for the photon to produce CC bar and look for the D plus D minus difference, because what happens, the 3-gluon versus 2-gluon exchange produces an asymmetry between the D plus and D minus. So actually, the interference between the Autoron and the Pomeron is very interesting, and you're seeing then the Autoron at the amplitude level. So that's interesting. Okay, another phenomena that just very briefly, something I worked on with Bjorkine and Goldhaber. So what people see in the data when they study things at CMS, they're surprised at high multiplicity events where they trigger on one particle, that they see a ridge on one side and a ridge on the other side in rapidity. So there's actually 2 different ridges, in fact. Now, it turns out then that what happens, BJ and Goldhaber and I discussed this, that when you, in fact, take the 2 strings, which is really, to me, just the confinement potential, and you collide them, then you get these high multiplicity events from one end to the other, and when you analyze them, you get this ridge phenomena. So that's very interesting. And then also, when you do electron-proton collisions, now you have another thing. The electron produces a photon, which produces a QQ bar. That has a string. It interacts with the string between the diquark and the quark. All sorts of interesting physics there. So you can see high multiplicity events and ridge events and measure new ways to measure the light front wave functions and so on. So I think that you want me to quit. Yeah. And so then you can measure this with charm quarks and see differences. You can control the axis of this guy, because if the electron scatters, it polarizes the photon out of the plane, and that produces a CC bar, which is back in the plane. So this guy's in the plane, so then you can actually tune the ridge direction and see it's in the plane of the scattering. And so that's there too. And you can also do this in neutrino reactions. Okay, let's see, 2 more minutes maybe? 2 more minutes, all right. So I like to quote this paper by Z, which he says this is one of the gravest puzzles of theoretical physics. He says that if you compute the Cosmogel constant from QCD, you get 45 orders of magnitude too big. If you do the electroweak, you get 10 to the 56. This is, and in Adam's talk, he talked about actually the vacuum has got all sorts of complicated dynamics. The moment you put that in, you get the 10 to the 45. You don't see that. So the string theory people, what do? They say, well, there's 10 to the 10,000 different string theories, and we live in one universe where the correction cancels out the gigantic numbers of things. However, in light front quantization, which we talked about here, the vacuum is trivial. It's causal. It's frame independent. There is no vacuum structure. All the physics that people associate with the vacuum effects are inside the hadrons and so on. And the Higgs theory, and I mentioned this in a previous talk, is actually not a vacuum oscillation Higgs. That's not the VEV. It's actually a constant zero mode. And that constant zero mode is actually just in the hadronic domain. That's all it is. You don't get anything like this. So Ed Witten says this is the most embarrassing problem in physics. That's what he thinks about these numbers. How can you get the number? He thinks it's down by 10 to the 120, because QED vacuums produce this huge thing. Nothing like that happens the moment you use the front form. There's no problem at all. We view the universe at fixed light front time. When you look through a telescope, you don't look beyond the speed of light. So everything is there. And the front form vacuum, light front vacuum, describes the empty causal universe. So there's 2 different definitions of the vacuum state. Most people think it's the lowest energy state of the instant form Hamiltonian. It's in fact in the front form, it's the lowest invariant mass state, and that's just 0. So the vacuum is just trivial in the front form. There's no bubble graphs. There's no graphs like this with electron, positron, photon, because all particles propagate with positive plus momentum. You can't start with 0 plus momentum and so on. Now, in Feynman rules, we have these vacuum graphs. However, if you remember, you're taught, in fact, maybe Adam will lecture on this, you divide out the vacuum graphs to maintain causality. You normal order the vacuum. So actually, the Feynman loop bubble graphs play no role in physics anyway. The front form knows that. You don't have to make any special thing. It's already normal ordered. And the front form vacuum then can simulate the empty universe. It's independent of the observer's frame. It's causal. It's the lowest invariant mass state. It has possible 0 modes, but that's irrelevant. Higgs theory is consistent with a trivial vacuum. QCD and ADS QCD in hadron condensates, all that physics. Gell-Mann-Oakes-Renner is satisfied. There's no vacuum matrix elements. QED vacuum, there's no loops that appear in the vacuum in light front, and you get 0 cosmological constant. The real question is how you get a non-zero value. That's the issue. How do you get a non-zero value? So in these lectures, I've talked about color confinement, a way to understand it, get the complete spectrum of the theory, get a good representation of not only spectroscopy, dynamics. It explains where the QCD mass scale comes from, this famous kappa parameter. Of course, it's a model. However, it seems to work remarkably well. Universal Regge slopes, massless pion. For a bound state, that's tremendous. I never saw anybody ever find that. The pi-rho splitting is exactly right. Dynamic spectroscopy, QCD couplings from low scales to high scales, and there's no condensates. So we've used conformal invariance that dictates anti-de Sitter space. We only predict ratios until you put the, you don't really care about the actual mass parameter. You could scale kappa any way you want. We have supersymmetric features of QCD when we implement superconformal algebra. You see that by the degeneracy of the meson, baryon, and tetraquark things. You get unique confinement potential, non-perturbative running coupling. Physics is independent of the observer's frame, just like Dirac said. Physics is independent of conventions. There's no, of course, pancakes. I think all of you are convinced that that's silly. Physics is independent of conventions, such as MS bar, that's the PMC. Nothing can depend on a human choice of a scheme. Zero cosmological constant for the light from vacuum. Leading to its factorization, breaking comes from initial state and final state reactions. That was a Sivers effect, diffractive processes, double Bohr molders. Nuclear shadowing and anti-shadowing is not in the nuclear light front wave function. It comes from these exotic effects of two-step, one-step interference. That's the only theory we have explaining that. And nuclear PDFs abatably do not base on those. Okay. So I will skip this. I'll just show this graph. This is what I realized that people can do eventually. Start with the quarks and gluons and sandwich the light front wave functions. Because now we know what they look like. We should be trying it, you know. And this is the famous equation that gives us the whole spectrum. And the super conformal algebra gives us this degeneracy of the fourplet. The tetraquarks are just as fundamental as baryons and mesons. We get this degeneracy. And I think I'm at the end. Here it is. Okay, thank you.